the second lecture. So I would like to talk a little bit about variational methods and applications. And yesterday there were some things I didn't prove. I didn't even give ideas of proofs. I will come back to that later on. Okay, so I will talk of the heat equation a little later in this talk. Okay, so I will explain what the variational method is and what the applications are. So let me remind you that I work with a compact Riemannian manifold. It's also assumed to be connected. So probably I will forget to mention it is connected and it's a smooth manifold. And if I consider a manifold with boundary, I will put the Dirichlet boundary condition. Okay, so I will just briefly recall what the variational method is. So for this, you introduce this L2, the L2 space on the manifold with the Riemannian measure. I will only consider real valued functions. That's simpler, and I have the associated norm. So unfortunately, I need some notations. And now I will consider also the completion of the smooth functions with compact support with the norm, which is the scalar product is the scalar product of the scalar product of UW in the one norm is the integral of the scalar product of the differentials. So G star is just the metric on the cotangent space plus the product of the function. So this gives a scalar product, and then you can look at the completion of the space. So of course, if M has no boundary, then this is just what is called the H1 of Mg. So that's essentially the space of functions which are L2 and which have derivatives in L2 in some sense. Okay, and when the manifold has a boundary, in fact, we have a smaller space, and this is the functions whose trace on the boundary is 0. So let me just mention this. This is so you see, if you take an L2 function, then you cannot, of course, you cannot say that the function takes values on a curve, for example, because a curve has measure 0. But if the function is a little more regular, then you can tell what the value of the function is on the hypersurface. Okay, and that's what the trace means. Okay, and this is just because we have more regularity than only L2. Okay, I mean, if you're not familiar with this, you can just forget this and think only in terms of the smooth functions with compact support. You forget compact support if the manifold is closed. Otherwise, you think of functions with compact support inside the manifold with boundary. And in fact, instead of working with Hilbert space, you will work with pre-Hilbert space. So it's essentially the same thing if you don't want to bother with these spaces. So now there is a very important integral, which is called the Dirichlet integral. And so that's d of u. Okay, let me just d of, yeah. I have read a lot these transparencies, and each time I read it, I notice there is some mistake. So, okay, so d of u is, let me write it a little bit differently. D of u is the norm of the differential of u You take the norm with respect to the Riemannian measure, the squared, and you integrate. Okay, that's the Dirichlet integral. And of course here there is a mistake. This you can also look at the bilinear form, and that's what is written here on the under transparencies. Here this should be a DUW. And there is yet another thing which is, that's just a notation, but that's important to have that. And that's what is called the Rayleigh Quotient. And that's just looking at the Dirichlet integral divided by the norm squared of the function, the norm in L2. And so what you can do, you remember I had this, this theorem. I don't remember if I have. Yeah. So the theorem is here. I had this, this theorem which tells you that if you take a compact Riemannian manifold, then you have a sequence, an infinite sequence of eigenvalues and on an orthonormal basis of eigenfunctions. And you can prove this theorem using the variational method. Okay? So I don't want to do that, to spend too much time doing this, but still I want to give you some idea of how one does this. And the idea for this, as is explained on the transparency, is that you will minimize the Rayleigh quotient on a chain of Hilbert spaces. Okay, so let me do this. So the first Hilbert space I just consider H. So I start from H. And then I consider the infimum of R of U, so the Rayleigh quotient, with U in H, and I take away the zero function, otherwise I have a trouble. Okay? So it turns out that that's the same thing, of course, as looking for the infimum of the Dirichlet integral for functions in H with L2 norm equals to 1. So you look at the sphere. Here you have something which is homogeneous of degree 1. If you multiply U by some A, then R of A times U is just R of U. So you can restrict at what happens on the sphere. And now, I mean, in this case, that's very simple because my functions here are non-negative. So it's clear that the infimum exists. And the problem is to show that, in fact, there exists a function at which the infimum is achieved. And in fact, that will be, in fact, a line. Okay, so let me just briefly sketch the proof. So the idea, I will work with this. So the idea is to say, well, there exists some sequence UN in H with L2 norm equal to 1, such that, let me call mu the infimum, so that mu is less than or equal to d of UN less than or equal to mu plus 1 over n. Okay, and then you have to use some functional analysis. Here, what this tells you, here, if you remember correctly, this thing here is just the squared, the L2 norm squared of the differential of U. So, in fact, what this implies that the norm, the H1 norm of U squared is less than or equal to mu plus 1. 1 is the square of this one here, plus 1 over n. And so this is less than or equal to mu plus 2. So this is bounded independently of n. And so you have to use some functional analysis which tells you that there exists a subsequence which I will denote like this, un comma 1, and there exists some, say, let me call it u in H, such that u converges weakly in H1, in the H1 topology. Okay, this means the following, that for any v in H, the scalar product of un1 v tends to the scalar product of uv, the scalar product H1. Okay? Okay. Now you have to use an important ingredient. Let me just go back here. It's probably better for the image. So you have to use a very important ingredient, which is just Ascoli's theorem to some extent. So which tells you that H, so this is H1 or H10, H embeds compactly in L. L is just L2. So this map here is compact. Compact means that you send a bounded set to something which has let's say, a bounded sequence to a sequence with converging subsequences. Okay? So, of course, here my subsequence is bounded also, and so what this implies, so this is, this is just some kind of Ascoli's theorem. Okay, so this tells you that there exists a subsequence, another subsequence. So this is a subsequence of un1, and there exists some v in L2, in L, that's L2, such that un2 converges in L2 to v. Okay, so now you have two things that you have to use. The first is easy. This implies that un2 converges weakly to v in L2. So weak convergence in L is the same as here, except that you put 0 here. So it's clear that strong convergence implies weak convergence. And now when you have an inclusion like that, the fact that un1 converges weakly to u, of course, for the subsequence, that's the same. And you also have that un2 converges weakly to u in L for the L2 topology. Okay, so this is because you have this continuous map. Okay, so now you can conclude that these two functions must be the same. Okay, okay, so finally you have obtained the following, that you have some sequence. Just forget subsequences now. I just forget the indices. So you have some sequence un, you have some u, and you have that mu is less than or equal to d un less than mu plus 1 over n. Un converges weakly to u. Un converges to u in L. Okay, this implies that u has L2 norm equal to 1, because the un had L2 norm equal to 1. That's here. So in particular, u is not 0. And now you have to work a little bit more That's easy. That's because mu is the infimum. So what you write is the following. You write that if you take some f in H1, if you take this squared, so this should be less than un 1 squared f1 squared. This is just Cauchy-Schwarz. But here you know that this converges to u scalar product with f. So that's the weak convergence here. And this, you know what this is. This is just d un plus norm of un0 squared. So this converges to mu because of this inequality, and this is 1. So this converges to mu plus 1. And now if you just replace f by u, when you go to the limit, what you get is that the norm of u to the fourth should be 1, should be less than mu plus 1, the norm of u squared. So you can simplify this. And now this norm, because of this inequality, must be bigger than or equal to mu plus 1. Okay? So this should be bigger than or equal to mu plus 1. This is the inequality over there. Well, no, this is because mu is the infimum of d of u, and so you have equality. Okay, so this implies that d of u is exactly equal to mu. And now there is a trick, which I will leave as an exercise. If this you can, of course, write like this. For any v, you can write that this is bigger than or equal to u plus tv 0 squared. And, well, if you develop this, what you will find, because you have a minimum here, at t equals 0, what you will find is that for all v, say in H, or even more simply, I can write this, you have that d of u v must be equal to mu u v 0. And this implies the most interesting thing. If you just integrate by parts, this tells you that Laplacian u is equal to mu u in the sense of distributions. Okay, which means that you integrate the other way around. So you have that u Laplacian v 0 is mu u v 0. Okay, so now you have to use some tools from EDP. Will tell you that if you have Laplacian is an elliptic operator, if you have this kind of relation, this implies that u must be a C infinity function. And so you have actually found a function u, which is a C infinity function, which is an eigenfunction of the Laplacian associated with mu, which is the infimum of the Dirichlet integral on this L2, on the sphere, on the unit sphere in L2. Okay. Okay. So now, what the idea is that you have one function So you have find your function u, which I write as a one-dimensional vector space. And now what you will do is essentially make the same reasoning by looking at the orthogonal space. And then you will minimize the Rayleigh quotient in the orthogonal part, and you will find a second eigenvalue, an eigenfunction, and you go on like this. Okay, so in this manner, what you do is you construct the sequence of eigenvalues and eigenfunctions. And then you have to complete the theorem, well, that's not written, but to complete the theorem, you have to prove that the eigenvalues go to infinity, and you have to prove that they have finite multiplicities, and you have to prove that you have an orthonormal basis, so that you have a big set of eigenfunctions. So how do you do that? To see that the eigenvalues, okay, let me just say why the multiplicities are finite. That's because on the eigenspace, because Laplacian u equals to lambda u, this means that the Dirichlet, that the H1 norm is proportional to the L2 norm. But you remember that I wrote that we have a compact embedding from H to L. So if you have something which is compact, it cannot have infinite dimension. So it tells you that the sphere for the L2 norm or for the H1 norm are essentially the same. So it must be a finite dimension because the embedding is compact. So this gives you finite multiplicities. Now, what happens if the lambda k were bounded? Well, that's not possible either, because you see, you will have your eigenfunctions, and you would have an infinite sequence of eigenfunctions which are mutually orthogonal, just because the Laplacian is symmetric, and then you would have exactly the same thing. I mean, you would bound the H1 norm of this family, and you would be able to extract a converging subsequence, but that's an orthogonal L2. That's orthogonal in L2, so that's not possible. And now, why is this an orthonormal basis? Is again because if this were not an orthonormal basis, then you would be able to find a vector, a function orthogonal to all these with a finite H1 norm, and this is not possible by the construction. You have to think a little bit. Okay, so this gives you a very simple proof of this theorem. And somehow it's interesting because it's more or less a kind of constructive proof. And, okay, no, I have to go back to some. Oh. Okay, now the second very important thing is that, you see, in this construction I explained, you first minimize the Rayleigh quotient, and you find the first eigenvalue and the first eigenfunction. And then, using the first eigenfunction, you will find a second eigenvalue and a second eigenfunction. And you continue like that. And the bad point is that you need to know the eigenfunctions if you want to take hold of the eigenvalues, and that's not good. So what the min-max and max-min say is that, in fact, you don't have to know the eigenfunctions. You have information on the eigenvalues only by considering the Rayleigh quotient, but instead of looking only on functions, then you will look at the Rayleigh quotient on spaces. Okay, so just forget the second one. So consider the first one. So what this says is the following: if the kth eigenvalue, and of course I should have written that here this only makes sense if you order the eigenvalues in the increasing order. So that's lambda 1 less than or equal to lambda 2 less than or equal, etc. So if you look at the kth one, then how do you find it? Well, you take the spaces of dimension k in H, or say in the say infinity functions with compact support, you take any vector space of dimension k, you look at the Dirichlet integral or the Rayleigh quotient on this space, you take the maximum, okay, and here with U normalized. Okay, so you are working in a finite dimensional space, so this is no problem. And then you take the infimum with respect to all the k-dimensional spaces. And if you do this, you don't have to know the eigenfunctions, and this gives you the kth eigenvalue in increasing order. Okay? Okay, maybe I will just leave the proof of this as an exercise. The idea, you have, in fact, two inequalities to write. So if you call, let me call mu k the right-hand side of the first equality of this here. So what you have to show is that lambda k is less than or equal to mu k, and you have to show that lambda k is bigger than or equal to mu k. Okay, so how do you do this? This one is easy. You just have to take the space, the k-dimensional space generated by the first k eigenfunctions. You just plug this in, and you have this inequality right away. Now, how do you find the first one? Well, you take any f, it's k-dimensional, and you say, well, in this k-dimensional space, there is a non-zero vector which is orthogonal to k minus 1, to the k minus 1 first eigenfunctions. Okay, and then you apply the construction, and you get this second inequality. So you have these very nice inequalities. Okay, so with this, I want to prove something which is very basic, very important, is that the least eigenvalue has a remarkable property, that any eigenfunction associated with lambda 1, the least eigenvalue, does not vanish in the interior of M. This, I must insist that this is true for functions. I mean, if you consider the Laplacian on forms, then that's not true anymore. Okay, so let me give you a short proof of this. I will make a figure of an interval. So assume that a first eigenfunction looks like this. Assume it vanishes. So, well, when you look at the Rayleigh quotient, in fact, it turns out that the Rayleigh quotient does not change if you take absolute value. You have to think that H1 functions, somehow you could think of functions which are C1 by parts. Okay, so if you have something like this, this is not so important. Okay, so if you do this, you will have this function here. Okay, and this function vanishes. Okay, but now what you can do is do the following. You can just cut off here and consider this new function. What happens if you cut off this part? Well, you see here the function is constant, so that the contribution to the numerator in the Rayleigh quotient is 0. So it's less than what happens with the original function. And now if you look at the denominator, then this function is bigger than this one. Okay, so in fact this function here, let me call it v. What happens is that r of v is less than r of u. Okay, so this cannot, I mean, if u minimizes r, then this cannot be true. Okay, so somehow this tells you that that's not completely rigorous, but I mean, you can, I mean, that's at least it gives a good vision of why this is true. Okay, so an eigenfunction associated with the least eigenvalue cannot vanish in the interior. Okay, then if it cannot vanish in the interior, it also means that the multiplicity of the eigenspace must be 1, because if it were at least 2, then you would have 2 eigenfunctions. One would be orthogonal to the other, and this cannot be true with functions which do not vanish. Okay? So this also implies that the first eigenspace has dimension 1, and this is why in the theorem I had lambda 1 strictly less than lambda 2. Then this is no longer true afterwards, but at least for this first one you have this. And the other property is that if you have a function which satisfies Laplacian u equals lambda u, if u does not vanish in the interior, then you know that lambda is not only an eigenvalue, that's the least one. Okay, because if you take any eigenfunction, I mean, if you take 2 eigenfunctions associated with different eigenvalues, they must be orthogonal. And if the function does not vanish, it means it cannot be orthogonal to the first one. So it must be the first one. Okay? So you have a way of knowing that a function is the first eigenfunction, or that an eigenvalue is the least eigenvalue of the Laplacian. So that's a very important thing. I think I will use that let me just give this right away. So an application of this is that if you have a domain with some symmetry, then the first eigenfunction must have the same symmetry. Okay, so let me state this like this. If M has a symmetry, then phi 1 inherits this symmetry. Well, why is that true? Just because if you have a symmetry, when you compose so you have phi 1, now you have your symmetry, let me call it sigma. Because the Laplacian is a natural operator, this tells you that this also must be an eigenfunction. So that's let's say that's the first eigenfunction. So this must be an eigenfunction, because sigma is an isometry. And of course, we have the same equality. So because the eigenspace is one-dimensional, this tells you that they must be proportional. And then if you assume, for example, that phi 1 is positive, this one must be positive, so alpha is positive. And if you normalize by the L2 norm equal to 1, then you see that alpha must be equal to 1. Okay? So this tells you that if you have the first eigenfunction inherits the symmetries of the domain, and in particular, if you have a domain with a rotational symmetry, then the function will have the rotational symmetry. So for example, I will use that later on. If you consider balls in, let me just state this. So assume, let me denote by M and K the simply connected model space with dimension K, no, with dimension N and constant curvature. Okay, so I think this is Rn, Sn, or Hn, depending essentially on the sign. If you can normalize K to be -1, 0, +1. So if you take a ball, so all the balls in this space are the same, with the same radius, I mean. Now, if you look at lambda 1, let's say with we will put D here to mention the Dirichlet condition of this ball. And if you take phi 1, the associated eigenfunction, then this must be a radial function. Okay, so in fact, it satisfies a second-order differential equation, ordinary differential equation, which I will write in a minute. Okay, so we have these important properties. Okay, another property which follows immediately from the min-max is that if you, let me stick like this, I mean, that's probably not optimal, but assume we have a Riemannian manifold, reasonable manifold, and you have two domains, two compact domains, two relatively compact domains, the manifold, and one is contained in the other. Omega 1 is contained in omega 2. Then what the min-max tells you immediately is that the first eigenvalue of omega 1 for the Dirichlet boundary condition must be bigger than the first eigenvalue of omega 2. Okay, this is just because you can view the C infinity function with compact support inside omega 1 as a subspace of the C infinity functions with compact support inside omega 2. Okay? And in fact, one has a little more, that's a little more difficult to prove, that if the interior of omega 2 minus omega 1 is non-empty, then you have strict inequality in here. Okay, so that's a very important property. Okay, so now that's another application. This is the so-called current nodal domain theorem. So, okay, so let me just explain what the theorem means. So the theorems tells you the following. So assume that you have Laplacian u equals lambda k u, you really have an eigenfunction u is not 0. Okay, and lambda k is the kth eigenfunction in the increasing order, eigenvalue in the increasing order. Okay, so what you can do is look at the connected components. You see, if I draw the picture in a domain, so here you will have u minus 1 of 0, and you look at the connected components of m minus u minus 1 of 0. So these are called the nodal domains. Okay, so now you can count the number of such domains. And what Courant's theorem tells you is that you have at most k such domains. Okay, so the number of connected components of the complement of the zeros of u is less than or equal to k. So you see that you have equality when you take the first, when you take lambda 1, you take the, okay? It just tells you that the function does not vanish, okay? Now if you take any eigenfunction with k bigger than or equal to 2, it must be orthogonal to the first one. Because the first one does not vanish, it tells you that the function must vanish. In fact, must change sign. So you have at least 2 nodal domains. Okay? Now so it's clear that you have at least, if k is bigger than or equal to 2, then you have at least 2 nodal domains. How do you see that you cannot have more than k? Well, that's relatively easy. I will not make the proof, but essentially the idea is that you assume that you have at least one k plus first here, And what you do is you look at the other one. So here, let's say you have 1, 2, 3, up to k. You look at the restrictions of the functions to all these domains, and 0 outside. So you have a family of k eigenfunctions which are independent because they have disjoint supports. And then you can play a little bit with the Rayleigh Quotient, and you can prove that you can construct a function which would be an eigenfunction for the kth eigenvalue, but then it would vanish on an open set, and this is not possible. I mean, that's another theorem that in fact eigenfunctions, they have a kind of unique continuation property, so they cannot vanish on an open set. Okay, that's how you can prove it. So this theorem is, so there is a natural question. The question is whether you can bound from below the number of nodal domains. And the answer to this question is no, you can't. And in fact, if you take, there are examples on the sphere, for example. If you take any eigenspace of the sphere with the eigenvalue very big if you want, as big as you want, and you can, in these eigenspaces, you can always find an eigenfunction with either 2 or 3 nodal domains. So that in general, you cannot say more than bigger than or equal to 2. That's essentially what okay? So that's very different from what happens in dimension 1. So in dimension 1, if you look, well, you can look at the trivial case, which would be this, because then you have, let's say, y of a equals y of b equals 0. If you look at this, you just have signed functions. Okay, but you can do something a little more complicated, and you can put some v here, some function v. So what happened is the following. So the picture is like this. So that's the first eigenfunction, and this is essentially what we have proved before. Then you have the second eigenfunction. In this case, in dimension 1, in fact, all the eigenvalues must be simple eigenvalues. And then the situation is so here you have 2. So here you have 1 nodal domain. Here you have 2. If you look at the third one, it looks like this. So in fact, if you look at Sturm-Liouville problems, the kth eigenfunction has exactly k nodal domain. Or you can formulate this differently. You can say here that the function has 0 plus, no, that's 1 plus 2 minus 1, zeros. So it has no 0 inside. Here it has exactly 1 0 inside. Here it has 2 zeros inside. So 1 is 2 minus 1, 2 is 3 minus 1, and the nth eigenfunction has exactly n minus 1, 0 in the open interval. Okay, n plus 1 if you take the endpoints. Okay, so that's a different way of looking at things, because in one case you look at the nodal domains, and the other case you look at the number of points where the function vanishes. So in higher dimensions, the idea is that maybe you should look at the length. For example, in dimension 2, you should look at the length of the nodal set. And there is a very nice theorem which is due to Brünig and Gromes. So I will state it very loosely, but the theorem tells you the following. If you have Laplacian u equals lambda u, then, so that's dimension 2. Let's say a Riemannian surface. Then the length of u minus 1 of 0 is bigger than or equal to some constant, well, somehow which depends on the surface, square root of lambda. So this tells you that maybe there will be few nodal domains, but then the nodal set must be very complicated. Okay, so this is not very difficult to prove. In fact, it's rather easy because you work in dimension 2, and the idea is to use isoperimetric inequalities. And well, the question in higher dimensions is rather difficult. And there has been some progress with lower and upper bounds in general, but with constants which are not always very explicit. So I would like to explain a theorem. Gérard convinced me that I should explain this theorem. So somehow this theorem is an application of the theorem I mentioned yesterday about embedding a Riemannian manifold by the heat kernel. Here I will use the eigenfunctions. Well, the theorem is not completely satisfactory, but it tells you the following. It tells you, well, take an n-dimensional closed Riemannian manifold and take an orthonormal basis of eigenfunctions. Okay? And then you take all the eigenfunctions up to a certain level. So for this purpose, you count the eigenvalues less than some lambda. Okay, so that's a number, n of lambda. And then you have n of lambda eigenfunctions, and you take these n of lambda eigenfunctions. Now you take something which lives in the projective space. This is just because I don't care about scaling. And you make this linear combination of the eigenfunctions. So you have some functions which is no longer an eigenfunction because that's a linear combination of eigenfunctions, but that's not an eigenfunction. And you look at the zero set of this function. So you can view this as depending on the parameters a1 up to a n of lambda. So now essentially what happens is that for almost all points in the projective space, this set Z sub A, the set of zeros of this linear combination, will be a reasonable set. And then you can compute, that will be a hypersurface, then you can compute its n-1 dimensional volume. And now you have a function which depends on the parameter A. You integrate this over the projective space. You divide by the volume of the projective space, so you compute the mean volume of these nodal sets. And what the theorem tells you is that when lambda tends to infinity, this mean volume there is some constant, is the volume of M times the square root of lambda. So this is a kind of very weak and loose generalization of this two-dimensional result. So the idea to do this is okay, let me just say something else. I have to yeah, let me just explain something which is probably well known to geometers. So let me just look at the sphere. I could look at the complex projective space or real projective space or quaternionic projective space as essentially a compact symmetric space of rank 1. But let me consider the sphere. So what happens with the sphere is that you have very big multiplicities. Okay, so if you take lambda, an eigenvalue of the sphere, so you have the eigenspace E lambda. So let me assume that I have an orthonormal basis. And then you can do something that you can, Okay, let me just say this is mg, because I could put the complex projective space, for example. So now I can do the following. I can send the manifold into the Euclidean space by x is phi 0 of x, phi n of x. Then when you do this, what happens is that you end up lambda of m is contained in the sphere with radius r, well, for the sphere, there's not really an embedding. You have to divide out by the antipodal map, so you have really an embedding from the real projective space, but otherwise, that's an embedding. So up to dividing by plus or minus 1 in the case of the sphere, you have an embedding. So let me just read this. When you pull back the metric from Rn plus 1, what you find is k, which is just lambda, that's the lambda here, r squared divided by n times the original metric, g. Okay, so that's very classical. I mean, people who work on minimal immersions know that also this gives minimal immersions. So now what happens, you see, if you take a linear combination here, this means that you will intersect the image of M by some hyperplane in the sphere. And then you can compute the image of lambda of M by integrating the hyperplanes, by integrating the volume of the intersection over the family of hyperplanes. So let me just write so this is called, Crofton So let me just write what this is. So if you look at the volume of the image of M associated with the Riemannian metric on Rn, then you find the following. You find that that's the volume of the sphere with radius r, so that's the same r. Here you have the volume of the n-1 sphere. You have 1 over the volume of the real projective space, and that's the integral over the projective space of the volume of lambda of M intersected by hyperplane. Okay, so you have your image in the sphere. To a point in the projective space, you associate a hyperplane. You look how this hyperplane cuts lambda of M. So this will give you a submanifold with a dimension 1 below. Okay. So you compute the volume with respect to the metric on Rn, and now you have a function of A, and you integrate this function over the projective space. And what Crofton's formula tells you is that you can recover the volume of the image lambda of M from the volumes of the intersection of this image with the hyperplane. And now the intersection of the image with the hyperplane, because of the definition here we give, is just the nodal set. you have a0 phi 0 plus a n phi n, and you take all this minus 1, 0, and this is exactly what is in here. Okay, so in the case of spheres, you have a kind of exact theorem. So in the mean, what you find is exactly that if you take in the mean the volume of nodal sets of eigenfunction of the sphere in an eigenspace, E lambda associated with lambda is just proportional to the square root of lambda. Okay, and how can you do that with this theorem? The idea is that you embed. I mean, you take a large number of eigenfunctions, and what happens is that, first of all, if you take a large number of eigenfunctions, you actually can embed the manifold, because if you take enough eigenfunctions, they will actually separate the points. And then what happens is that you fall almost on the sphere. In fact, you arrive on something which is like a bumpy sphere. And this you can control using the heat kernels, for example. And then using these techniques of embeddings that I mentioned last time, then you can prove the theorem which was on the slide. Okay, so that's a kind of weak answer to this reciprocal to the occurrence theorem. Okay, so now I would like to come to eigenvalue comparison theorems. So, first of all, I will consider bounding eigenvalues from above. So somehow this is rather easy. It doesn't mean that you don't have to be clever, but it's somehow easy because you have the min-max. So if you are clever enough, you find a nice function, you plug it into the min-max, and you get a nice estimate for the eigenvalues. Okay, so that's mainly the ideas here. So let me just first prove the theorem. So what the theorem says is the following. So Mg is a complete Riemannian manifold. In fact, what is important, I just work locally. So what is important is that I assume that the Ricci curvature is bounded from below. And then you take a ball in the manifold. And what the theorem tells you is that you can compare the first eigenvalue with Dirichlet boundary condition in the ball in your manifold with the first eigenvalue in the model space of the ball with same radius in the model space. Okay, that's what the theorem tells you. In fact, this theorem is a little bit complicated because, you see, I have no assumption on R. There is another theorem of Cheng which gives a bound from below. But this theorem only works with balls within the injectivity radius. So here I have no assumption on the injectivity radius. And then what the theorem tells you also is that if you have equality, I mean, this inequality is good, because if you have equality, this exactly means that your ball must be isometric to the ball in the space with constant curvature. So let me briefly explain how one can prove this theorem. I will use it in the next theorem. So recall what I explained before, that if you take a ball in a space with constant curvature, then the first eigenfunction with the Dirichlet boundary condition must be a radial function. Okay? So let me look at what happens in the model space. So let me define the function sk of t. So as usual in Riemannian geometry, that's sine of square root of k times t divided by square root of k, or t, or hyperbolic sine of square root of absolute value of k times t over square root of absolute value of k. So, I mean, that's of course for k positive, k zero, and k negative. And ck is just the derivative of sk. So now if you look in the model space, the metric, if you look at the metric, well, if you look at, let me just look at the Laplacian maybe. So I have the ball, I have lambda 1 with Dirichlet boundary condition on this ball, and I have phi 1, the corresponding eigenfunctions, and I can assume that phi 1 is positive. So what I claim is that because it's radial, if you write the Laplacian in polar coordinates, what you find is that phi satisfies the equation that the second, okay, let me just call it phi, it will be simpler, plus n minus 1 ck sk plus lambda 1 okay, I think that's correct, but let me just check. Okay, and in fact, you have to understand something that, well, you see here, when t goes to 0, you have a singularity here, and you know that the first eigenfunction must be regular. So, in fact, what this implies is that it's as if, let me just write it like this, that the derivative of phi at 0 must be 0, and phi of r is 0. Okay, so that's not a regular boundary value problems. Okay, so this is of course because I consider Dirichlet boundary condition on the boundary of the ball, and this is because of regularity. Okay, and now if you can rewrite this as follows. That's important. You can write this as sk n minus 1 t phi dot of t, so d dt plus lambda 1 sk n minus 1 t phi of t is equal to 0. That's the same thing. But this is important because if you look at this, you see this I assume is positive. Okay, because that's the first eigenfunction. This function is positive, at least if before we get to the conjugate point, and this is positive. So this means that this derivative here must be negative, and this derivative starts from 0. So if it's decreased, I mean, this one must be negative. So if you look at this starts from 0. So this means that the function phi, the derivative of phi must be negative. So the picture is like this. You have here 0, r, the function vanishes here. Here it's like this. Okay. So now what you do, and so now I will. That's not necessary. I will do it because that will make my life simpler. But let me assume that r is small enough. So essentially, r is smaller than the injectivity radius. Well, this is not necessary because, in fact, we will work only on with the Rayleigh quotient. But okay, so now you look at what happens in M. So you take your ball, and you have the exponential map, And I will look at the exponential map as going from the tangent space, which I write like this, to M by TU, a unit vector exponential x of TU. Now what happens is that the important thing is to look at the Riemannian measure in these coordinates, and the Riemannian measure is some function which depends on x, tu, dt, du, where du is the Riemannian measure on the unit sphere here. Okay, so now what I want to do is I want to look at the function capital phi, the composition of the small function phi here, this eigen function with the exponential map. And in fact, if you don't want to write that you are smaller than the injectivity radius, in fact, what you have to do is just cut off the functions once you reach the first cut point. Okay, and so now you can compute on the ball. You can compute this integral. Okay, and this integral is just the following. It's just the integral with my assumption here. Otherwise, you have to write down something which is more complicated. But so you have the integral over the unit sphere, the integral from 0 to r, and then this is just the derivative squared of phi, because this function only depends on the distance to the point. And then here you have to write theta tu dt du. And you can also write phi squared, and that's the same thing. Okay, so now let me look at this function here, okay, at this integral. So if you look at the integral, you can integrate by parts. So you can write that the integral from 0 to r of the derivative of phi squared so this is phi dot phi theta between 0 and r plus the integral from 0 to r of phi, and then you will find the second derivative of phi minus the first derivative, the derivative of theta with respect to t, like this. So this is just integration by parts. Now if you look at this integral, you see that okay, this vanishes at 0, this vanishes at 0, so nothing happened at 0, and phi vanishes at r. So this term here disappears. Okay, and now you use something. So I'm lucky because I still have this on the board. So the derivative of the first eigenfunction in the ball in the model space is negative, so minus the derivative is positive, and now you at least will use the assumption. Okay, so the assumption is just Bishop theorem. Bishop's theorem, which tells you that theta is less than the same thing in the model space. Okay, so now if you multiply by minus phi dot, which is positive, then this will be preserved. And then this integral here, what you will get, dt, then here I will be able to substitute this function here by this one. But this, in fact, the theta is related to the sine functions which I used earlier, and that's exactly what you expect. So here, what you find is exactly lambda 1 of the ball, and then the integral of phi dt. So now, if you integrate on the unit sphere, and if you compare with the denominator, then what this gives you is that the Rayleigh quotient of your function capital phi, this one, must be less than lambda 1 of d. So by the min-max, the lambda 1 of the ball in the manifold M is less than this Rayleigh quotient, and so you have the inequality. Okay, and now you have this theorem, Cheng-Gromov. In fact, Cheng proved the theorem, but he missed the point. Okay, let me explain. Okay, so now what we want to do is to use Cheng's theorem, to use this estimate from above, to give an estimate from above of eigenfunctions of M of an eigenfunction, of a large eigenfunction, eigenvalue. Okay, so the idea is as follows. So you have your manifold M, and then the idea is to cover the manifold by small balls. Okay, so I will put as many balls as possible. Okay, so I consider the families such that the balls are pairwise disjoint. Okay, so now by some abstract nonsense, you have that there exists a maximal family. Okay, so there exists a maximal family let me call it x1 till xl of epsilon, a maximal family of balls that are pairwise disjoint. Now, the fact that the family is maximal tells you that when you look at the balls with radius 2 epsilon, then the balls must cover M. Okay? So that's a classical covering argument. So maximal implies that M is the union of the same balls but with radius 2 epsilon. Okay? So now I can say two things. First of all, I can give some estimate of this number. Okay, so we'll write that the volume of M is less than the sum of the volumes of the balls. And now these volumes, again, using Bishop theorem, this volume must be less than the volume of the same ball in the model space. Okay, so this is less than L of epsilon times what I will call B sub k of 2 epsilon, which is thus just the volume of the ball of radius 2 epsilon in my space with constant curvature k. Okay? So now what I claim, you say, so if I take a J like this, so J less than or equal to volume of M divided by the volume of bk to epsilon, so this will be less than L epsilon. And now what I can do, you see, I will work in the, I have these these balls. Now I take the balls with radius epsilon, and I will consider the space generated by the Dirichlet first eigenfunctions for each of these balls. Okay, so I have linearly independent functions because I will extend them by 0 outside the balls. So I have L epsilon functions with disjoint supports. So these functions, they generate a space of dimension L epsilon. And then if I plug this into the min-max, so this tells you that lambda L epsilon, lambda of M, must be less than the maximum of the eigenvalue, or the first eigenvalue with the Dirichlet boundary condition for these balls. But this is what Cheng's theorem tells you. So this is less than lambda 1 d of bk epsilon. Okay, so now you have to think a little bit. So you think that J goes to infinity, and you will choose epsilon, which depends on J and M, in such a way that J is exactly equal to volume of M divided, I should say here, volume of M. Of course, K and divided by volume of bk to epsilon. So this is the epsilon here. Okay, and okay. So now you will have. So what does this mean? So essentially, this tells you when epsilon is small. So this is J is something like volume of M, a constant which depends on N and K, volume of M. And here I will have epsilon to the minus N. Okay, because when epsilon goes to 0, this behaves like epsilon to the N with some constant. Okay, and now I will have like that lambda J is something like this, asymptotic 2. And now when epsilon goes to 0, you have to think that the manifold, the Riemannian manifold is very much like Euclidean space in which you have the dilations, so that the first eigenvalue here behaves like 1 over epsilon squared. Okay? And so, so lambda j is less than, okay, so that's another constant. So this will be j over volume of M to the 2 over n, right? Because I want 1 over epsilon squared, so I already have the 1 over. And to have the squared, I have to take the square and take the nth root. So the squared and the nth root. Okay, so what this tells you is that asymptotically, the eigenvalues don't grow faster than j to the 2 divided by n. And if you remember, we had this Weil's asymptotic formula, which tells you that this power is the right power. Okay? So somehow what we have reached, like with this estimate, is a nice upper bound for the eigenvalues in terms of volume and the Ricci, lower bound on the Ricci curvature. Now I should say a couple of things. Okay, yeah. I have to go back to my notes. What do I want to say now? Okay, okay. So that's it. That's not too bad. So we have a nice upper bound. Now the question is whether one can have a lower bound of this type. Now for the lower bound, there is an example which maybe I will leave it for you to check. You can look at this family of manifolds. You take the n-1 sphere with some parameter times the circle, and if you look at this, so that's a very simple manifold. That's a product manifold, so we know how to compute the eigenvalues. You can see that the way I put the constant is so that the volume of MA is constant. And you see that the Ricci curvature of MA is always non-negative. Now, if you look at the eigenvalues, and in fact, you only have to see that, you see in a product, the eigenvalues of a product are just the sum of one eigenvalue here and one eigenvalue here. In particular, I can take the eigenvalue 0 here, so I have all the eigenvalues of S1. And the eigenvalues of S1 here are, what is it? Something like that, where P is an integer. Okay, so what you can do with this example is you can show that you cannot have an estimate from below like this in general. Okay, so you cannot hope to have an estimate from below with the volume here. Okay, and last time I mentioned this theorem, and if you look at the corollary, what this theorem tells you is that you can bound the eigenvalues from below in terms of the Ricci, lower bound of the Ricci curvature, so that's the same as here. but you cannot, you don't put the volume, what you have to put is the diameter. And somehow, there is another counterexample which goes back to Calabi, which essentially tells you that you cannot hop better than the diameter. So somehow this theorem, what this theorem tells you is that you have the best possible estimate for the eigenvalue from below. So you have the right power in J, and the dependence on the lower bound of the Ricci curvature and upper bound on the diameter. Okay, so you see that you have two different results depending on whether you look at upper bounds or lower bounds. Okay, so I was a little slower than I had thought, so maybe I will leave for next time. I would like to explain this. In fact, I would like to explain something simpler, which is not to consider all eigenvalues, but the first eigenvalue on the closed manifold is 0, so that's very simple to estimate. And then you look at the next one. We know that the next one is strictly positive, and the point is to estimate the first non-zero eigenvalue from below. Okay? And so what one can prove under the same assumptions as in the preceding theorem, if the minimum of the Ricci curvature times the diameter squared is bigger than something, then the first non-zero eigenvalue is bigger than some constant times 1 over the diameter squared. Okay, so this is simple to prove, and to prove this, I will use a well-known technique, which is using isoperimetric inequalities. So this was, this was proved for the first time by Faber and Kran in the 1920s, something like that, for the eigenvalues of a plane domain, that the first eigenvalue of a plane domain is always bigger than or equal to the first eigenvalue of the disk with the same area. So that's essentially the same kind of theorem. So that's what I want to explain next time, and then I will probably go to some other topic. Okay. So if you have questions, maybe it's what is on the menu. Okay, so see you tomorrow, probably in another room.